Welcome to This Explainer. Today, we're diving into exactly how AI agents automatically fix failures and why the SRE, the site reliability engineer of the future, might no longer be a human being. Picture this scenario for a second, okay? It's 3 a.m. Deep inside a massive enterprise data center, the quiet hum of servers is suddenly shattered by blaring digital alarms. Red alerts are flashing wildly across the monitoring screens. Your CPU usage has spiked to 100%, critical APIs are timing out, Kubernetes pods are trapped in this vicious crash loop, and to top it all off, your database replication has completely failed. An engineer's phone is just vibrating relentlessly on their nightstand. A massive, catastrophic outage is happening in real time. But then, the unthinkable happens. The alarms just stop. Out of nowhere, the dashboards turn completely back to green. And the crazy part here, before a human engineer could even wipe the sleep from their eyes, grab their laptop, or SSH into a single server, the system magically healed itself. There was zero human intervention, none. So you really have to ask yourself, who or what just fixed the entire system?
Well, the culprit behind this midnight tech mystery is an AI agent. We're going to completely unpack this today because what we're talking about isn't some distant science fiction. It's a massive paradigm shift happening right now in infrastructure automation. We're literally crossing the threshold into an era where systems can observe, reason, and repair themselves autonomously.
All right, let's jump into section 1, pain points of traditional debugging and the race against downtime. To really grasp why this is such a game changer, we have to look at the traditional workflow. A human has to wake up, totally groggy, check the Grafana dashboards, sift through thousands of lines of logs, manually SSH into Linux servers, attempt to restart services, and maybe even roll back a deployment. It takes minutes, often tens of minutes, just to figure out the root cause. Resolving an incident is fundamentally a race against downtime. Now, compare that to the AI workflow. It can detect the anomaly, reason through the root cause, and execute the exact fix, all in under 30 seconds. And why does this matter? Pure scale. If you're running a massive e-commerce platform, a global CDN, or an AI SaaS platform, a single minute of downtime can cost millions of dollars. Human reaction times are just fundamentally too slow for modern scale. Moving right along to section 2, system anomaly detection. Let's look at exactly how the AI actually knows the system is broken. Now, the AI isn't using some kind of dark magic. It's constantly digesting thousands of telemetry metrics in real time. Sure, it monitors standard infrastructure health, things like CPU, memory, and disk I/O. But it goes so much deeper than that. It's looking at API latency, TCP retransmissions, Kubernetes events, deep kernel-level eBPF telemetry, and even user click streams and database query patterns. What you should really take away from this is that the AI establishes a highly complex baseline model of what normal looks like for your specific system. If your normal API latency is, say, 30 milliseconds, and today it suddenly jumps to 300 milliseconds, the AI instantly flags that anomaly. There's a core philosophy that captures this perfectly. Without telemetry, AI is blind. The AI uses this massive ocean of observability data to do something we humans really struggle to do quickly under pressure. It cross-analyzes. When things break, it deduces the context. Is this just one specific pod crashing, or is an entire node blowing up? Is it a Redis timeout, or are we looking at a malicious DDoS attack? Or, hey, is it just a bad code deployment from an hour ago? It doesn't just see the failure. It actually reasons through the why. Which brings us to section 3, executing auto repair. Enter the decision engine. Let's break down how the AI navigates real-world disaster scenarios. Say a Kubernetes pod is stuck in a crash loop. The AI analyzes the recent deployment, discovers a memory leak, and bam, it automatically triggers a rollback to the previous healthy version. Or what if a Linux server experiences a massive CPU spike? The AI scans the process tree, analyzes the system calls, confirms it's an abnormal and potentially malicious fork, and immediately kills the process while blocking the offending IP address. And if your primary database latency spikes because of massive storage I/O, the AI instantly switches to a replica database and seamlessly redirects traffic. It is resolving these incredibly complex, highly stressful scenarios in under 30 seconds. The end user on the other side, they feel absolutely nothing. So what's under the hood? Section 4, the core tech driving AI and unmasking the architecture. To make all of this possible, enterprises rely on a highly logical 3-step pipeline. Step 1 is observability. Enterprises deploy tools like Prometheus, OpenTelemetry, and eBPF so the AI agent has crystal clear visibility into everything. Step 2 is the brain, LLM, and reasoning.
Modern agents use large language models to read through messy Linux logs, complex stack traces, and Python exceptions to truly comprehend the root cause. And finally, step 3 is the automation engine. The AI decides on the action, sure, but it relies on standard, battle-tested tools like Ansible, Terraform, or Argo CD to actually execute the physical changes. It is a brilliant synthesis of cutting-edge AI and traditional automation. But it's not all sunshine and rainbows. Section 5. The biggest hidden risk. What happens when the AI gets it wrong? Objectively speaking, the biggest risk of auto-remediation isn't that the AI fails to fix the system, it's that it might break it entirely. Imagine a scenario where a marketing campaign goes viral and you get a massive, totally legitimate surge in traffic. If the AI incorrectly flags this normal surge as a DDoS attack, it might respond by blocking your entire CDN. It could kill perfectly healthy server processes, roll back normal versions, or cut off database synchronization. In trying to protect the infrastructure, its automated cure literally becomes far worse than the disease, taking down the entire system in a totally self-inflicted outage. So how on earth do we prevent that? Well, enterprises mitigate this massive risk by utilizing a vital safety net known as keeping a human in the loop. In this hybrid model, the AI does all the heavy lifting. It ingests the metrics, reasons through the logs, and formulates the exact repair plan. But instead of executing it blindly, it just proposes the fix. A human engineer receives that detailed proposal, reviews the AI's logic, and must ultimately confirm and approve it before any change is deployed. This saves us precious diagnostic time while ensuring we don't accidentally nuke our own servers. Let's look ahead. Section 6, the autonomous era and the unmanned data center. We are rapidly speeding toward a reality with almost no human engineers on the floor. Instead, an army of AI agents will be in charge, auto-patching security vulnerabilities, actively hunting for threats, and even auto-rebuilding entire Kubernetes clusters from scratch if they fail. As we enter this new era where the true maintainer of the system is just another AI, we're left facing a profound dilemma. Exactly how much control should we hand over to the machine? Thanks for joining me on this explainer. I'll catch you next time as we continue to unpack the future of technology.